Here's a video to help with converting from grams of one thing to grams of another. Now the question says, approximately 1% of the world's energy consumption each year is used to react nitrogen gas in the air. The air you're breathing right now is 79% nitrogen, with hydrogen gas, which you can get from the gases that you get out of the ground when you're drilling for oil, for example. And from that you can make ammonia, nitrogen and hydrogen. And with ammonia, you can make fertilizer. Ammonia can be used to make amino acids that then can make proteins in plants. The ammonia that's made from that feeds about a third of the world's population. A third of everyone alive today is alive because of this reaction on the screen. Now, this is what the reaction looks like. It's not the most visually stunning reaction because both nitrogen and hydrogen gas are clear gases. But what's happening here is this scientist is passing those gases through an iron catalyst as he heats it up under pressure. And when he does that, the nitrogen and hydrogen are turning into NH3, which is ammonia. Now that's usually done at really high pressures and temperatures, which is what requires all the energy. It's around 150 to 250 atmospheres. And 1 atmosphere is the pressure that surrounds you when you're at the beach. And 400 to 500 degrees Celsius, or between 750 and 930 Fahrenheit. So very hot, very high pressures. And it's done at plants that look like this. Each of these is a plant that does that reaction and collects the ammonia. It requires 1% of all the world's energy used each year. But, interestingly, there are microbes that do the same reaction in the nodules of plants. These microbes exist in soils, and they infect the roots of certain plants and form a sort of symbiotic relationship. The microbes have an enzyme that's able to do that same reaction, but at room temperature and atmospheric pressure. So all the energy that human beings need to make the reaction, these microbes can do without that energy. And they can make the ammonia that allows the plant to then use that ammonia as a fertilizer to make amino acids. And the plants that are infected by this microbe tend to be full of more proteins. So for example, beans, nuts, and peas. Now if a human being could figure out how that enzyme works, they could save the world huge amounts of energy. In this question, though, we want to imagine if we're doing this reaction and we're trying to make fertilizer to feed people, how much can we make given that we have a certain amount? So here, the question is asking how many grams of NH3 can be made if we have 92.17 grams of hydrogen. Now, there are key words in this that should stand out to you. If a question ever gives you grams of one thing and asks for grams of another, you're going to solve it in a very particular way. Okay, so here they're asking grams of ammonia, and the number they're giving you is 92.17 grams of hydrogen. Whenever they give you grams of one thing and grams of another, you're always going to follow this procedure. You'll go from grams of the first thing to moles of the first thing, moles of the first thing to moles of the second thing, moles of the second thing to grams of the second thing. That's the procedure. Now each of these arrows represents a conversion, and for every conversion you need a conversion factor that relates the two units. So for this first arrow, we need a conversion factor that relates grams of hydrogen to moles of hydrogen. Now in this molecule, we only have hydrogen, but we have 2 of them. And to figure out how much 1 mole of hydrogen weighs, we'd go to the periodic table, we'd look at the box that has the element in it. The number below the symbol is the number of grams in 1 mole of that element. So 1 mole of hydrogen would weigh 1 gram. Because we have 2 hydrogens in this molecule, it would weigh 2 grams. So there'd be 2 grams of hydrogen in every 1 mole of hydrogen. That takes care of our first conversion. How about for our second conversion, this middle arrow? For that, we need a conversion factor that relates moles of hydrogen to moles of ammonia. And to get the relationship between those, we're going to look at the coefficients in the balanced equation. Those are those big numbers in front of a molecule in the balanced equation. So what number is in front of H2 in the balanced equation? 3. So that means for every 3 moles of hydrogen, we're going to look for the big number in front of NH3 in the balanced equation, 2 moles of NH3. So that gives us our second conversion factor. Now for the third arrow, our third conversion factor. For that, we need to know how moles of NH3 relate to grams of NH3. Now we have two elements in this compound, and we want to think about them separately. We've got nitrogen and we've got hydrogen. If we had 1 mole of this compound, we would have 1 mole of nitrogen, because there's no subscript here. That implies that we just have 1 nitrogen. Now, to figure out how much a mole of nitrogen weighs, we'd go to the periodic table, look at the number below the symbol on the periodic table. That's the number of grams 1 mole of nitrogen weighs, 14 grams. So 1 times 14, we have 14 grams coming from the nitrogen in ammonia. Again, if we assume we have 1 mole of NH3, that means we'd have 3 moles of hydrogen. To figure out how much 1 mole of hydrogen would weigh, we'd go to the periodic table, look at the box that has hydrogen in it. The number below the symbol is the grams in 1 mole. So that's 1 mole of hydrogen would weigh 1 gram. Since we have 3 hydrogens here, it's going to be 3 times 1, or 3 grams coming from hydrogen in this molecule. So if we had 1 mole of this molecule, 14 grams would be coming from nitrogen, 3 would be coming from hydrogen. Altogether, that's 17 grams. So there are 17 grams of NH3 in 1 mole of NH3. All right, now that we have our conversion factors, we can take the number they originally gave us, 92.17 grams of hydrogen. And every time you do a conversion, you write a multiplication sign, a fraction bar, and the units you start with, which here are grams of hydrogen, go on the bottom of the fraction so that they'll cancel out. Now I'm going to fill that first fraction in with my first conversion factor. Next to grams of hydrogen, we'll go 2. Going over the fraction bars, like going across the equal sign, and on top, I'll have 1 mole of hydrogen. Grams of hydrogen cancel out. I'm left with moles of hydrogen, but I don't want moles of hydrogen, I want grams of ammonia, so I have to do another conversion. Every time you do a conversion, write a multiplication sign, a fraction bar, and the units you start with, here moles of hydrogen, go on the bottom of the fraction so it cancels out. Now I'm going to fill that second fraction in with my second conversion factor. Next to moles of hydrogen goes the number 3. Going over the fraction bar is like going across the equal sign, and on top you'll have 2 moles of NH3. Moles of hydrogen cancel. I'm left with moles of NH3, but I don't want moles of NH3, I want grams of NH3. So I get to do another conversion. Every time you do a conversion, write a multiplication sign, a fraction bar, and the units you start with, here, moles of NH3, go on the bottom of the fraction so that it cancels out. Now I'm going to fill that third fraction in with my third conversion factor. Next to moles of NH3 goes the number 1. Going over the fraction bars like going across the equal sign, and on top I'll have 17 grams of NH3. Moles of NH3 cancel. I'm left with grams of NH3, which is exactly what I wanted. And the way you'd plug this in a calculator is you'd have 92.17 times 1, enter, divided by 2, enter, times 2, enter, divided by 3, enter, times 17, enter, divided by 1, enter, and you're left with 522 grams of ammonia. So if you have 92.17 grams of hydrogen, you can make a maximum of 522 grams of ammonia. All right, similar thing. In this case, though, we want to use 63.5 grams of nitrogen, and we want to know how many grams of hydrogen you would need. So it's a conversion problem, and we want to look for what units they're asking for and what number they're giving us. Now they give us the number 63.5 grams of nitrogen, and the units they're asking for, how many grams of H2. Whenever they give you grams of one thing and ask for grams of another, you always follow this flowchart. You go from grams of the first thing to moles of the first thing, moles of the first thing to moles of the second thing, moles of the second thing to grams of the second thing. Each of those arrows represents a conversion, and for every conversion we need a conversion factor that relates the two units. So for this first arrow, we need to know how grams of NH2 relate to moles of NH2. Now there's only one element in this compound, but we do have 2 atoms of it. So if we had 1 mole of N2, we would have 2 nitrogens, 2 moles of nitrogen, because that's the subscript. Then we'd go to the periodic table, and we'd see that below the symbol there's a number 14. That's how many grams 1 mole of nitrogen weighs. So since we have 2, altogether it's 2 times 14, or 28. There are 28 grams of N2 in 1 mole of N2. That's our first conversion factor. Now for our second conversion, the middle arrow. For this, we need to know how moles of N2 relate to moles of H2. And to get the conversion factor for this, you're going to use the coefficients, the big numbers to the left of each compound on the periodic table. So in front of N2, nothing is written. And that means that we only have 1 of this. So there's going to be 1 mole of N2. You might wonder, why isn't it 0? Well, if it were 0, you wouldn't even write N2. You wouldn't have any at all. But because you have the N2 there, you know you at least have 1 of those molecules. In front of H2, which is the other thing we're interested in, is the number 3. So we'll put 3 moles of H2. And that's our second conversion factor. For our third conversion, we need to know how moles of H2 relate to grams of H2. And for that, we'll use the periodic table. We know there's only 1 element here, hydrogen, but we do have 2 hydrogens. If we look at the box of the periodic table, we see that each mole of hydrogen weighs 1 gram. Since we have 2, it'd be 2 times 1, or 2 grams. There are 2 grams of H2 in every 1 mole of H2. Now that we have our conversions, we can take the number they gave us, which was 63.5 grams of N2, and we can do a conversion. Every time you do a conversion, write a multiplication sign, a fraction bar, and the units you start with go on the bottom of the fraction so that it cancels out. Now I'm going to fill that first fraction in with my first conversion factor. Next to grams of N2 goes the number 28. Going over the fraction bar is like going across the equal sign, and on top you'd have 1 mole of N2. Grams of N2 cancel out. We're left with moles of N2, but we want grams of H2, so we have to do another conversion. Every time you do a conversion, write a multiplication sign, a fraction bar, and the units you start with, which here are moles of N2, go on the bottom of the fraction so they cancel out. Now I'm going to fill that second fraction in with my second conversion factor. Next to moles of N2 goes the number 1. Going over the fraction bar is like going across the equal sign, and on top you'll have 3 moles of H2. Moles of N2 cancel out. You're left with moles of H2, but we want grams of H2, so we have to do another conversion. Every time you do a conversion, write a multiplication sign, a fraction bar, and the units you start with, which here are moles of H2, go on the bottom of the fraction so they cancel out. Now I'm going to fill that third fraction in with my third conversion factor. Next to moles of H2 goes the number 1. Going over the fraction bar is like going across the equal sign, and on top you've got 2 grams of H2. Moles of H2 cancel out. We're left with grams of H2, and the way you'd plug this in your calculator is you take 63.5 times 1, enter, divided by 28, enter, times 3, enter, divided by 1, enter, times 2, enter, divided by 1, enter, and you should get something like 13.6 grams of H2. So that's how many grams of H2 you'd need if you wanted to use all of your 63.5 grams of N2 to make fertilizer so that people could eat. All right, what if you want to make 100 grams of ammonia? That's how much you need to feed this community. How many grams of N2, nitrogen, will you need? So it's a conversion problem. What do they give you? 100 grams of ammonia, NH3. What units are they asking for? Grams of N2. Whenever they give you grams of one thing, here grams of ammonia, and ask for grams of another, here grams of N2, you always follow this flow chart. You go from grams of the first thing to moles of the first thing, moles of the first thing to moles of the second thing, and moles of the second thing to grams of the second thing. Now each of these arrows represents a conversion, and for every conversion you need a conversion factor that relates the two units. So for this first conversion, the first arrow over here on the left, how do grams of NH3 relate to moles of NH3? Well, we have two elements in this compound. We have nitrogen and we have hydrogen. If we assume we have 1 mole of NH3, we only have 1 mole of nitrogen because it doesn't have a subscript. And each mole of nitrogen, we can go to the periodic table and see the number below the symbol is 14. Each mole of nitrogen weighs 14 grams. Since we only have 1 of them, altogether that's 14. Now for hydrogen, if we had 1 mole of NH3, we'd have 3 times as much hydrogen, 3 hydrogens for every 1 of this whole compound. So we'd have 3 moles of hydrogen. We can look on the periodic table. The number underneath the symbol is the number of grams in 1 mole for that element. So 1 mole of hydrogen would weigh 1 gram. Since we have 3 moles, altogether that would weigh 3 grams. So if we had 1 mole of NH3, we'd have 14 grams coming from nitrogen, 3 grams coming from hydrogen. Altogether, that is 17 grams. So there are 17 grams of ammonia in 1 mole of ammonia. So that's our first conversion factor. Our second conversion factor, we need to know how moles of NH3 relate to moles of N2. And for this, we look at the coefficients in the balanced equation. What's the coefficient in front of NH3? It's 2. So we're going to write 2 moles of NH3. For every, what's the coefficient in front of N2? None is written there, but we do have the N2. That means it's just 1. So 1 mole of N2. So for every 2 moles of NH3, we would need 1 mole of N2. That's our second conversion factor. Now for the third one. For that, we need to know how moles of N2 relate to grams of N2. Now we only have nitrogen here, but we do, if we had 1 mole of this compound, we would have 2 moles of nitrogen, twice as much, because there are 2 nitrogens in every 1 of this whole thing. We can look at the periodic table. Underneath the symbol is the number of grams in 1 mole, so that's 14. Because we have 2 moles, we'll have twice that much, 2 times 14, or 28 grams. There are 28 grams of N2 in every 1 mole of N2. So there are our conversion factors. Now, we can take the number they gave us all that time ago, 100 grams of NH3. We can do a conversion. Every time you do a conversion, write in a multiplication sign. A fraction bar, the units you start with, your grams of NH3, go on the bottom of the fraction so it cancels out. And I can fill that first fraction in with my first conversion factor. Next to grams of NH3 goes the number 17. Going over the fraction bar is like going across the equal sign, and on top you've got 1 mole of NH3. Grams of NH3 cancel out. We're left with moles of NH3, but we want grams of N2, so we get to do another conversion. Every time you do a conversion, write a multiplication sign, a fraction bar, and the units you start with, which here are moles of NH3, go on the bottom of the fraction so it'll cancel out. Now I'm going to fill this second fraction in with my second conversion factor. Next to moles of NH3 goes the number 2. Going over the fraction bars like going across the equal sign, and on top you'd have 1 mole of N2. Moles of NH3 cancel out. We're left with moles of N2, but we want grams of N2, so we get to do another conversion. Every time you do a conversion, write a multiplication sign, a fraction bar. Those units that you started with, yep, moles of N2, those are going to go on the bottom, so they'll cancel out. Now I'm going to fill that third fraction in with my third conversion factor. Next to moles of N2 goes the number 1. Going over the fraction bars like going across the equal sign, and on top you'll have 28 grams of N2. Moles of N2 cancel. We're left with grams of N2. That's exactly what we wanted. Victory is sweet. And to plug this in a calculator, you'd take 100 times 1, enter, divided by 17, enter, times 1, enter, divided by 2, enter, times 28, enter, divided by 1, enter, and you should get something like 82.4 grams of N2. That's how much nitrogen gas you'd need if you wanted to make 100 grams of ammonia, NH3, so that you can make fertilizer, so plants could grow and feed a community and make people's lives wonderfully happy. Thank you so much for your attention.